Hey class, today we're going to start talking about acids and bases, and we're only going to get a little bit of this on exam 3. The final exam will have the rest of the material on acids and bases. So only lectures 30 and 31 talking about acids and bases will be on exam 3. So just to let you know that. Okay, let's get going here. All right. So let's start off doing a review quiz from the last lecture. Okay, so this says if this reaction is at equilibrium and we decrease the volume of the container, what happens? Okay, so we talked about a couple ways to know which way the reaction will shift if you decrease the volume of the container. One way is just to memorize what happens. The other way, which I like to do, is to look at the number of moles. So we have gases here, so we have 1 mole of gas on the left side. Let's just say that's in a 1 liter container. That would be a 1 molar solution, basically. On the right side, we have 2 moles of gas in a 1 liter container would be a 2 molar solution. Okay, so if we decrease the volume, so let's say on the left side, we now have this 1 mole in a 0.5 liter container. That would be a 2 molar solution. And so we went from 1 molar to 2 molar. And on the right side, we had 2 moles in a 0.5 liter container. We'd have a 4 molar solution. Okay, so here we went up by 1 molar. Right side, we went up by 2 molar. So we went up more on the product side. So we'd shift the reaction to the left, making more reactant. So let's see, nothing happens, more products are formed. That's not true, we're forming more reactants. The reaction releases heat. Okay, so to decide if this is true, we need to look at our delta H. Delta H is greater than 0, which means it's a reactant. And since we're shifting to the left, we're creating more reactant, so we are creating more heat, so C would be true. Equilibrium does not shift to the right, and there's definitely enough information, so there we go. Okay. All right, so we're going to talk about acids and bases now. You're going to see this a lot in Chem 285. Acid-base chemistry is all over the place. So this is going to be a good introduction. So there's kind of 3 definitions of acids and bases. After you're familiar with them, you'll kind of see that it's really more like 3 different perspectives or ways of looking at acids and bases, and some are more general than others. So the original definition is called the Arrhenius definition, or Arrhenius acids and bases. And this is a very specific type of definition. This only applies when your solvent is water, and basically says that acids and bases are a specific type of electrolyte. And we'll talk about these in this slide. The other definition is a little more general. It's a Bronsted-Lowry definition, and it works with any solvent. So we're getting a little more general here. Then the most general definition of acids and bases, which apply really to anything, is the Lewis acid-base definition. And this is something that you'll use a lot in organic chemistry, and you'll learn it in organic chemistry. We're not going to talk about it much in this one because it really applies more for organic molecules. So we're just going to focus on the Arrhenius and Bronsted-Lowry definitions for acids and bases. Okay, so starting with Arrhenius acids, the official definition would just be an electrolyte that produces H+ ions in water. So for example, if you put HCl in water, it's going to dissociate into H+ ions and Cl- ions, okay? So by definition, this is an electrolyte because it dissolves in water, right? And it produces H+ ions, so it's an Arrhenius acid, okay? So HCl is an Arrhenius acid. Hydrocyanide or hydrocyanic acid also does the same thing, and carbonic acid does the same thing. We're going to talk about how to name acids in this lecture as well. It has a sour taste when you're, if you taste it, like lemons or oranges or anything like that. If there's enough sugar, it would cancel out the sour taste. Like an orange may not totally taste sour, but the citric acid, if you isolated it out of an orange, would taste sour. Like in a lemon, you can definitely taste sour. Okay, and then it turns litmus red. So litmus is just an indicator. It's basically a material that you can drop a liquid on, like water, and it'll tell you if that water is acidic or basic. So you'll see that term litmus, but it's really just an indicator that back in the day before pH, like fancy pH meters and stuff like that, it was a really quick and easy way to tell if something's acidic or not. You just dab it on the litmus and it would tell you. Okay, and then acids are kind of like the opposite of bases. They neutralize bases. We'll talk about how that neutralization occurs as well. Arrhenius bases is going to be, like I said, kind of like the, it's kind of like an opposite, I guess, of an acid. And so these are electrolytes that produce OH minus ions. So right now it's hard to see how these are opposite of acids, but it's kind of helpful to view the OH minus ion as kind of the other pair to a H plus. But anyway, just know electrolytes that give off OH minus ions are going to be Arrhenius bases. For example, sodium hydroxide is soluble, or when it's placed in water, it dissociates into sodium ions and OH minus ions, and this is called hydroxide. Okay. Okay. So you have this electrolyte that dissolves in water and produces OH minus ions. So by definition, it's an Arrhenius base. Okay. Calcium hydroxide is as well. So they kind of taste bitter or chalky. So like tum, if you ever had a tum, it's kind of a basic, it's sodium carbonate. It's more of a basic molecule, so it definitely tastes chalky and neutralizes the stomach acid. Okay, so it turns litmus blue and then neutralizes acids. Okay, all right. So just some kind of other notes here to recognize. So acid-base indicators, we talked about litmus. So these are molecules or materials that are going to change color in the presence of an acidic or basic solution. So again, they're used to quickly determine if something is acidic or basic. The most common one that we'll talk about is litmus. So this is the molecule for litmus. And so depending on if it's in contact with a base or an acid, it's going to have different colors. So if it's in contact with a basic solution, it's going to be blue, or an acidic solution, it's going to be red. Okay, we'll talk about that a little more, but for right now, that's all we really need to know about litmus. And that's the only indicator really. You don't need to know the molecule or anything, just know that blue turns litmus, or basic solutions turns litmus blue, and acidic solutions turn litmus red. Okay, and then neutralization. So we talked about how acids produce H plus and bases produce OH minus. So if you take an H plus and you add it to an OH minus, you get 2 hydrogens and an oxygen, so that's water, right? And water is basically the standard for neutral. So what is neutral? So later we're going to look at pH scales and stuff like that. But you have a neutral stage, and then you have basic on one end of the spectrum and acidic on the other. Okay, so acidic would be like full H plus ions, basic is OH minus, and then in the middle, kind of between these two, is your neutral, and that's water. And again, we'll talk about pH in lecture 34. So for this third exam, for right now, just know that acids and bases neutralize each other, basically. Okay. All right, go ahead and try this quiz. Okay, so if we're looking at this, NaCl, when it's placed in water, is going to dissociate into Na and Cl, Na plus ions and Cl minus ions. Nickel hydroxide would dissociate into nickel 2 plus ions and OH minus. Calcium sulfate is going to dissociate into calcium ions and sulfate ions. And then nitric acid is going to dissociate into H plus ions and nitrate. Okay, so this one here produces an H plus, so it's going to be an acid by definition. This one here produces an OH minus, so it would be a base. And then these other two, because they don't produce H plus or OH minus, these are just gonna be electrolytes or salts, okay? Well, these are salts right here, but they produce electrolytes basically, these two, okay? Okay, so now talk about naming acid. There's really, at this point, since you've already learned to name polyatomic ions and covalent compounds, it's a pretty simple transition here. So when you have an ionic compound that contains H plus and an anion, okay, so the acid comes from the anion name. So that's what you need to remember. I think there's 3 points here. So that's the first one. Second one is acids containing an anion ending in IDE are named with the prefix hydro and ic. So for example, we have this HCl molecule. So normally you might name it like hydrogen chloride. And so chloride, again, we're looking at the anion when we name acids. So chloride has an IDE ending. So you're gonna put the prefix hydro and the suffix, I believe is the correct term, suffix ic acid, okay? So the only thing that stays is this chlor, okay? So that's right here. We have hydrochloric acid, okay? Cyanide is another anion that we've learned. So it's gonna be hydrocyanic acid, right? Cyan is the only thing that stays there, okay? All right, and then the other last bullet point here is if it ends in ATE or ITE, okay? So you basically have 3 situations. Either it ends in IDE, ATE, or ITE. So if it's ATE, it's going to be converted into ic acid, and if it's ITE, it's going to be an us acid. For example, chlorate, okay, that's an ATE ending. So we'll swap the ATE with ic acid, and instead of chlorate, it becomes chloric acid. Okay, and then chlorite, right? The ITE is going to be replaced with us, and we're going to get chlorus acid. Chlorus acid is how you'd actually say it. I was just accentuating that. And one thing I wanted to note here is that it only becomes an acid when there's no charge on it. So for example, let's take CO3 2 minus, right? This is going to be called carbonate. And then if we had HCO3 minus, right, we've learned that this is called hydrogen carbonate. Okay, so this shouldn't be new, or you could call it bicarbonate. Carbonate. Okay, but when you add enough protons to where there's 0 charge here, so like H2CO3, okay, there's no charge here now because we neutralized all the negative charges. That's the point at which it becomes an acid. So carbonate, it gets changed into ic, right? So this now becomes carbonic acid. Okay, so just recognize that if just by adding a hydrogen doesn't necessarily give it the acid naming. It's only when you add enough hydrogens to where there's no charge here. Okay, and you'll definitely get some practice with that. But if you know your polyatomic ions at this point, it's a pretty simple transition. You only need to remember these 3 new rules for IDE, ATE, and ITE. Okay. All right, let's go ahead and try some of these out here. So if you want, you can pause the video and try these out before I give you the answer. So the first one here is HI. So you, again, isolate the anion part. So that would be H or I minus. If you named this before as like a covalent compound, this would be hydrogen iodide, right? And if we remember that the acid is named after the anion, so it's going to be named after this portion. Iodide has an IDE ending, so that means you're going to give, you're going to take the IOD, you're going to add hydro at the beginning, and then ic acid. Okay, so hydroiodic acid. Okay, H2CO3. Okay, so if we isolate the anion here, we have carbonate, right? CO3 2 minus. And then we learned that the 8 gets turned into ic acid. So it becomes carbonic acid. And then try this one. Okay, so if we isolate the anion here, we're going to have hypobromite, right? BRO minus. And the ITE gets converted to us acid. And we keep the hypo in this case because we're really just taking the ITE and converting it into us acid. So it's hypobromous acid. Okay. All right. Cool. So yeah, just a lot of practice with that is going to help. I think you'll get some of that as you go through the homework. Here's a big chart. You should know how to name everything on this chart, and not that you need to like sit there and memorize it right now, but you should have already had all these polyatomic ions memorized. So just by knowing those 3 new rules would allow you to name anything on this chart here. Okay. All right. The other one you may not know at this point is acetate. I can't remember if I asked you to learn that one or not. I'm kind of blanking right now, but at this point I don't really remember asking you to learn acetate, so I'd probably just give it to you on the exam. Okay. All right, some common bases. So we learned how to name acids. Bases are going to be easier. Bases are named just as any other ionic compound. So you have the name of the cation followed by the name of the anion. And in a base, the anion is always hydroxide, OH. At least in the bases that we're going to be talking about in this class. Okay. So sodium hydroxide, or if you have a K, right, that's potassium hydroxide, barium hydroxide, same rules. And again, if you have a cation where the charge can change, like iron, then you would include the Roman numerals. So same as naming any other ionic compound, basically, up to this point. Okay, so now let's talk about the Bronsted-Lowry acid-base definitions. So in these definitions, basically all there is that acids donate a proton and bases accept a proton, okay? Protons are, you've probably already seen, but denoted by H+. So hydrogen atom, right, is number 1 on the periodic table. It has 1 proton and 1 electron. All right, well, if you remove this electron, then you now have a H with a plus charge, and all that is really just a proton. So you use the term, you'll hear the term proton and H plus used interchangeably because they're the same thing. Okay. So an example of this is like if you put HCl in water. HCl, or hydrogen chloride or hydrochloric acid, is going to donate its proton. Right, we already kind of talked about how HCl splits up into H plus and Cl minus ions. So it gets rid of this proton and water grabs it. And so you have this hydronium ion. You will also see hydronium interchanged with H plus sometimes. Okay, these are essentially the same thing for what we're looking at here. Okay. you just see hydronium because we're mixing it with water here. And so water will actually accept that proton. So we would say that HCl is the acid because it's giving up the proton. And since water is accepting a proton, it's the base. And you can tell if if you're looking at this and you're like, how do I know that hydrogen chloride or HCl gives off a proton? Well, I give you the products here, right? So you can see as you move over here, well, now chloride's on its own, which means it lost a proton, and the water actually gained a proton. So you can see that water accepted a proton, therefore it's the base by definition, and the hydrochloric acid donated a proton, so it's the acid by definition. Okay, here's another example. Okay, so ammonia. If you look at the products here, you can see that ammonia went from NH3 over to NH4. So it actually gained a proton, right? And if you gain a proton, you're a base, right? Bases are proton acceptors. And then water actually went from H2O over to OH minus, so it lost a proton. And then things that donate or lose protons are acids, okay? So water is our acid and ammonia is our base. So water could be an acid or a base, just depends on the equation you're looking at. Okay, so go ahead and try this quiz out here and see how we're doing. Okay, so the question says, in this following reaction, which compound is acting as a Bronsted-Lowry base? So Bronsted-Lowry bases, again, are going to accept protons. So if we look at the nitric acid, HNO3, and we follow the NO3 anion to here, you can see that it lost a proton. And the NO2, you can see that it actually picked up that proton, okay? So this was the proton donor, which is the acid, and this is the proton acceptor, which is the base, which is what we're asking for. So NO2 minus would be our base, okay? Alrighty, so now conjugate acid-base pairs. So when you're dealing with Bronsted-Lowry acid-base reactions, you're always going to have an acid and a conjugate base, and a base and a conjugate acid. And what that is, I'll show you here. So I've already kind of shown you, but so HF, if we follow it to the right side and look for the anion, we can see that we lost a proton. And you can see that the ammonia actually gained a proton. And so these are called acid-base pairs. So for example, HF is the acid on the left side. And if you did this reaction in the reverse direction, you'd find out that fluorine gains a proton to be in the reverse direction to become HF. So it's going to be considered the base on the right side, so it's called the conjugate base. On the left side, you can see that ammonia gains a proton, and molecules that gain protons are bases. Okay, and then if we looked at NH4, you can see that as it moves over to the left side, it's losing a proton, so that would be considered the conjugate acid. Okay, so these two, this right here is this right here is a conjugate pair. And these ones here, that's a bad one, are conjugate pair. I think there might be a graphic that shows this better than I've drawn it. But basically, an acid and its conjugate base are going to be a conjugate pair, and then the base and the conjugate acid are going to be a conjugate pair. And really all this is saying is that HF is going to lose a proton and become fluoride, and in the reverse direction, it would actually gain a proton and become HF, so it's a conjugate base. So you can just kind of follow the arrows and say this is one base, and then this is another base pair. Okay. Okay, let me back it up and let the slide. So you have a conjugate acid base pair 1, right? And then another base pair 2. And so really you're just looking for common anions or common, I guess, core units in these acid base pairs. Okay. So just a note, and I've kind of already said this, but the conjugate base of any acid is simply that acid with a proton removed. So HF here, the conjugate base of this acid is going to be that anion without the proton. And then for water, in this case, water is the base because HF is the acid. And so the conjugate pair is just going to be with an extra proton. So you can switch between conjugate base pairs by adding or removing a proton. So that's how you would, I guess, know that those are conjugate base pairs. For example, HF and water are not conjugate base pairs, right? Because simply adding and removing a proton would not get you between those two things. The only way to get, for example, from HF to F is by adding or losing a proton. Okay, so that would be kind of another definition of a conjugate acid-base pair. All right, go ahead and try this one out here. The question says the conjugate base of bicarbonate. Okay, so if it's asking for the conjugate base of bicarbonate, it's going to be inferring this is the acid. Okay, acids donate protons. So if this donated a proton, it would become CO3 2 minus. And then that acid without its proton, this would be referred to as the conjugate base of that acid. So A. Okay. All right, go ahead and try this one. So this one says, what's the conjugate acid of bicarbonate? Well, that infers that if you're asking for the acid, conjugate acid, then this is going to be the base. And bases accept protons. So if you added a proton to this, you would have H2CO3, right? So that would be C. Okay, cool. All right, so that's kind of a quick rundown on definitions. And so hopefully after this lecture, you're able to name different acids and bases, and then identify if something's an Arrhenius acid or an Arrhenius base, and identify if something is a Bronsted-Lowry acid or Bronsted-Lowry base, and identify conjugate acids and bases and their those pairs. So anyway, hope that was helpful, and we will catch you next time.